A good afternoon. I hope y'all are doing well. I hope you enjoyed the opportunity to sleep in if you got to, or just slowly get into your day-to-day if you didn't have to do any of the CASP testing stuff. You know, so hopefully that was kind of nice. A little bit of a break from our normal schedule. So today what I want to do is try to get through a quick review of everything we've seen so far from the beginning of the school year. It's going to be kind of like trying to drink from a fire hose. It's going to be a lot of information. I put it into a PowerPoint presentation that we're going to run through. The presentation is also, son of a gun. Oh yeah, that comes. Sorry, someone from attendance is trying to call me again in the middle of class. I don't know why they keep doing this. And it comes through my headphones really loud. Okay, anyway, this presentation is already loaded into Canvas under the Things You Might Need module. It's the very first module if you go into the modules. I'll also have it posted and loaded up on today's date in the calendar. We probably won't be able to finish it today. It's all a big amount of stuff, but we're gonna see what we can get through. I suggest looking and listening and only taking notes on things that you're like, oh my god, I totally forgot that. I really want to remember that. Jot that thing down. But I don't want you to try to write all of this down because again, we'll have access to it after we talk about it. If you have questions, you need clarification on anything, please ask. Stop me in my tracks and ask. All right. So other than that, we're going to get this thing going. See if everything wants to cooperate with me today. We'll find out. I think it will work. Let's see. It's thinking. I think it's working. Yeah. It looks like it's working. All right, awesome. Excellent. So here we go. It's time to review what we've seen so far. All right. Each chapter kind of covers a big main topic here. All right. Chapter 4 was sampling and surveys and experiments. It was the first thing that we covered. We'll get into some specifics on all of these later. Chapter 1, how to describe and display categorical and quantitative data. This is where we looked at graphs and tables and charts and things on, we first introduced the normal distribution, all kinds of fun stuff. Actually, not normal distribution, that came in chapter 2. Percentiles, mean, median, range, IQR, standard deviation, density curves, and normal distribution. We covered a lot of little things within chapter 2. All right, chapter 5, all right, we skipped chapter 3. And that's, for some reason, many people who teach AP Stats from this textbook do chapter 3 at the very end. I'm not sure why it's chapter 3 for that reason, but you know, we skipped it. We'll come back around to it here towards the end of the semester. All right, chapter 5 was probability, simulations, conditional probability, and independence. This is when we finally started getting into like some major calculations. All right, chapter 6, all right, beginning of second semester. We did discrete and continuous random variables. We looked at transforming and combining random variables, binomial random variables, and geometric random variables. Chapter 7 was sampling distributions of sample proportions and sample means. Chapter 8 was confidence intervals for estimating population proportions and population means. Chapter 9 was significance tests for testing claims about a population proportions, population means. And the chapter we just finished, chapter 10, comparing two populations or groups through confidence intervals and significance tests. All right, so these are the chapters and things within them that we covered. This isn't covering absolutely every little piece of definition or detail that was covered in those chapters. If you need a more thorough review of any of the chapters, I suggest going back to your notes, going back to the resources in the previous semester's class, and looking at those things if you need more in depth than what we're going to do today. All right, so we started with chapter 4. All right, we started with chapter 4. All right, we had sampling and surveys to start. How to sample. We had convenience samples, voluntary response samples. Those both usually result in a bias. We then started looking at random sampling, simple random samples, and SRS. Stratified random sample, cluster sample. We considered biases such as undercoverage, non-response, and other forms of response bias. Right? Like how you word a question could result in bias. That's another type of response bias. Right? We then looked at experiments. Right? The second part of chapter 4 was how do we conduct an experiment? Right? We have an observational study versus an experiment. Right? The observational study is just kind of like looking and see what happens and taking notes and saying, okay, this is what happened. An experiment is specifically like purposefully having something done to some of the individuals, whether that's a treatment or something else, right? The experiment has some purpose behind it. Right, we have treatments, experimental units, and subjects. We looked at how to experiment well. We need random assignment. We need comparison, control, and replication. Those are the 4 pieces of a well-written and put together experiment. We always want to use a completely randomized design when we can. We have to consider things such as the placebo effect, whether or not we want to do a double-blind or single-blind study, and what becomes statistically significant, which now we have the tools to actually test for significance. Right? We can use block and randomized block designs and matched pairs design, which again comes back later when we think about doing matched pairs T procedures. And then finally, our scope of inference. Remember, the scope of inference is like based on how the experiment is set up or how we've collected our data. What type of inference are we allowed to make? Right? Can we make inference about the entire population? Can we only make an inference about the people that participated in the sample, in the study? Right? Things like that. Again, we have just some quick little images here to show the difference between a regular SRS, a stratified sample, and a cluster sample. Right? Stratified sample is grouping people together based on a common characteristic and then sampling randomly from those strata. The cluster sample is when you group people together based on location and then randomly select which clusters will participate in the sample. Right? With a cluster sample, the entire cluster is part of the sample. Whichever cluster is selected, everybody works in that experiment. Everyone participates. The clusters that are not selected, none of those people participate. All right, we have our random experiment, our completely randomized design of an experiment. We use these little arrow diagrams to kind of show how we've randomly assigned these things and what we're going to do, right? We randomly assign students to the treatments, so we randomly select students to be in group 1 and group 2, and then flip a coin to decide which group gets which treatment, right? And we compare our results. We can also do a block design, right, where we split students up by academic year. So we have blocks of academic year, so freshmen and sophomores, right? And then within those blocks, we then randomly assign those students to the treatments. That would be a block design. Each block gets both treatments, or any number of whatever treatments you have. And that one came in really slow. We also have the matched pairs design, all right? This is when essentially your blocks consist of 2 individuals that are similar, or 2 treatments being given to a single individual that you will then compare and have a difference, right, at the end between the 2 treatments. There's our matched pairs design. A matched pairs kind of blocking here results in a 1 sample T procedure. when finding a confidence interval or significance test. We then moved into chapter 1, which was exploring data. All right, we wanted to make sense of our data. We have individuals and variables. We can have categorical variable and quantitative variables. And then we have a distribution of those things. You remember, categorical variables are things that are categories, like colors. I cannot add up color names and find the mean of a color. Right? Quantitative variables are things that it makes sense to find an average of. Right? Values, numbers, right? Test scores are quantitative. Right? We can usually take a category and create some sort of quantitative value that goes along with it. Right? So there's that. Right? Categorical data can be displayed with bar graphs, pie charts, two-way tables, and marginal distributions. We also have conditional distributions and association. Quantitative data, we can use dot plots, histograms, stem plots, back-to-back stem plots, split stem plots, shape, center, spread, outliers. We use SOCS or CUS to completely describe a distribution, right? We have shape, center, spread, outliers, right? All those things. Our distributions can be symmetric or skewed. We can have unimodal, bimodal, or multimodal distributions. When we describe quantitative data, we must describe the center, which would be mean or median. The spread, we can use range, IQR, or standard deviation. We want to identify outliers. Our common method would be to use 1.5 times the IQR rule. Box plots from the 5-number summary, and we can compare distributions using histograms or box plots or dot plots or any of these things and look at their shape, center, and spread. As a quick review, categorical data, we can use pie charts or bar graphs. Bar graphs, the order in which the things are labeled on the horizontal axis is not important. I can rearrange those to change the shape, so it does not have a specific shape. If I wanted to, I could change the histogram or the bar graph on the screen and have it go B, D, E, C, A. The data wouldn't change, it'd still represent the data, but I've changed the shape. So we do not describe categorical data with shape. It doesn't make sense to, we can change it. We have a two-way table here comparing two categories, and then we have values along with those categories, which allow us to do marginal distributions or conditional distributions. And when dealing with quantitative data, we can make box plots, which looks like that in the picture there. Right. We can do a stem and leaf plot. We can make a histogram. The major difference between histograms and bar graphs is that histograms need to touch. One bin ends where the next one begins. It is continuous. The only time you have a gap between bars is if you have nothing in that bin. So if your bins are have 5 units in width, so your first one goes from 0 to 5, right? And then 5 to 10, 10 to 15. If you have no values that are greater than 5 but less and less than or equal to 10, then that bin is empty. You will not have a bar in that space. Then it'll pick up on the next one. But if you have values in each of the bins, in each of the widths, then the bars should be touching. Okay. Chapter 2, modeling distributions of data. Right. We want to be able to describe the location in a distribution. This is where we come up with percentiles. We can have cumulative or relative frequency, standardized score. Z-score is a very common way to find the location, relative of a normal curve. And we can also transform our data. Essentially, standardizing a score, standardizing a value, is transforming that data to the standard normal curve. All right. We use density curves in the normal distribution a lot. All right. The density curve has an area of 1 under the curve. The mean and median of the density curve depends on whether or not it is skewed or symmetric and things like that. All right, recall in a symmetric distribution, the mean and median should be in the same place. In a skewed distribution, the median should kind of split it in half, and then the mean will go in the direction of the tail. The tail will pull the mean that way, away from the median. All right? We have our normal distribution, and we use the notation n parentheses mu comma sigma, right, which is mean and standard deviation. Those two numbers will completely describe a distribution that is normal. The 68, 95, 99.7 rule applies to our standard normal curve. That means 68% of our data is between one standard deviation on either side of the mean. 95% is roughly between two standard deviations, and 99.7 is roughly three standard deviations. All right. When we're dealing with the standard normal curve, we typically will use table A and use z-scores to compare different things. When doing normal distribution calculations, we're finding the proportion of a curve based on a given value, finding a value given a percentile or proportion of a curve. We can work backwards from having the proportion under the curve back to a z-score and then unstandardize that to get an original score. We can start with an original score, standardize it, and then find the proportion under the curve. Right. And then lastly, sometimes we need to assess normality. This condition comes up when dealing with sampling distributions of means, confidence intervals for means, and significance tests for means. We need to assess normality quite a bit. Things should be approximately symmetric and bell-shaped, close to the 68, 95, 99.7 rule, and we can use a probability plot, which is kind of like if it ends up being a straight line, that's showing that it is normal. Right? If we get a curved line from a probability plot, that's showing that it's probably not normal. Right? And your calculator can do these things based on given data. And here's a picture of our 68, 95, 99.7 rule. And the formula to standardize a score, where x is the original score, mu is the population mean, and sigma is the standard deviation. Then we get into chapter 5, which is probability. All right, we have randomness, probability, and simulation. Probability is always between 0 and 1 and describes the proportion of time a random outcome would occur in the long run. I made a typo, sorry about that. All right, simulations can allow us to model long run behavior and imitate chance behavior. This could be useful. We have software that can do simulations for us. All right, we have specific probability rules. All right, we have our sample space. That's a set of all possible outcomes. Like when you roll a dice, there's 6 sides to a single dice. There's 6 possible outcomes. Right. When you roll 2 dice, there's 6 sides on each dice. There's 36 possible combinations, possible outcomes. Right. Probability model consists of a sample space and a probability for each outcome. Right. When you roll a single dice, labeled 1 through 6, each side of the dice has an equal probability of showing up, 1 in 6. When you increase that to 2 dice, you now have 36 possible outcomes. And each of those individual outcomes has an equal probability of occurring. But then if we start doing, okay, well, what's the sum of the 2 dice? Then the sums, the value of the sum of the 2 dice will then have, there's only one way to get a sum of 2. So 1 out of 36, right? There's 2 ways of getting a sum of 3. The first dice has a 1, the second dice has a 2, the second dice has a 1, the first dice has a 2. So we have 2 out of 36, and we can then fill in the probabilities of each of those possible outcomes in the sample space. Right. An event is any collection of outcomes from some chance process and a subset of samples of the sample space. So again, the event could be the sum of our 2 dice is less than or equal to 7. And we could use our sample space and the probability of each of those outcomes occurring and add them up to determine the probability of that single event. If all outcomes in the sample space are equally likely, the probability that event A occurs is P of A equaling the number of outcomes in event A divided by the total number of outcomes in the sample space. Right, we can just kind of add things up. And then 2 events are mutually exclusive if they have no outcomes in common. And for example, if event A is the sum of the 2 dice is less than or equal to 6, and event B is the sum of the 2 dice is greater than or equal to 7, Those don't have any intersection. There are not any event between those two outcomes or between those two events that are common. Those would be mutually exclusive. They can't both happen at the same time. A little bit more in probability. All right, we have thing freaking out here. Where'd it go? Hello. Can you guys see this? Yeah, okay. The screen I have set up to like preview it just went blank, so as long as you can see it. Okay, so we have some more probability rules. We have the complement rule. That is the probability of the complement of event A is 1 minus the probability of event A. So if event A is having the sum of the two dice being less than or equal to 6, the complement of event A is the dice being greater than 6, the sum of the two dice being greater than 6. Probability of the complement is 1 minus the probability of the original event. We use this complement rule a lot, especially using table A, because sometimes we're being asked to find the probability of Z being greater than a specific value, and table A only provides us with values less than. So instead of finding the proportion greater than, we just say 1 minus the proportion less than, and we get our solution, the complement. All right. We have the addition rule for mutually exclusive events. That is the probability of A union B, or A or B, is the sum of probability A plus probability of B. And this goes for mutually exclusive events. So if the events have no outcomes in common, we want to know the probability of either of those two events happening, then we just add the probability of each individual event. We have the two-way tables and the general addition rule, which the general addition rule works regardless of the events being mutually exclusive. Right? When finding probabilities involving two events, a two-way table can display the sample space, making probability calculations easier. Right? The general addition rule for two events, if A and B are any two events resulting from some chance process, the probability of A union B, or A or B, equals the probability of A plus the probability of B minus the intersection of those two events, P of A and B. So we add up the probability of each individual event and subtract the probability of the thing that they have in common, so we don't count it twice. Right. Venn diagrams can also help determine probabilities by modeling the sample space of a chance process involving two events. You can sometimes make that into 3 events or more. You remember Venn diagrams are the little like intersecting circles that we put in like a little box. We then have our conditional probability and independence. The notation P, parentheses B given A, that little up and down bar says given A, represents the probability that event B occurs given that event A has occurred already. The probability of A given B is equal to the probability of A and B divided by the probability of B. So the probability of both events happening divided by the probability of B happening. We can also write this probability of B given A is equal to the probability of A and B divided by probability of A. All right, so regardless of how this is, the numerator will be probability of A and B. The denominator will be the probability of the second event listed in the A given B, otherwise the given event, the one we know happened. All right, we have chapter 5, a little more probability. We have conditional probability and independence, right? We have our general multiplication rule. The probability of A and B is equal to the probability of A times the probability of B given A, which is just a rearranging of previous rule we saw. Right, so if we know the probability of A and we know the probability of B given that A occurred, right, we can find the probability of A and B. When chance behavior involves a sequence of outcomes, a tree diagram can be used to describe the sample space. So it's kind of like when your chance behavior involves like making choices along the way. Right, so we start with a thing and we have two choices. You can pass or fail, right? If you pass, you then have these other two events that can happen, and if you fail, you have these other three events that can happen. Each of those things has a probability attached to them based on their sample space. We can then follow that tree diagram and kind of multiply out the probabilities to get probability of a certain series of events happening. When knowing that one event occurred does not change the probability that another event occurs, we say the two events are independent. Right? When two events are independent, the probability A given B equals the probability of A, and the probability of B given A is equal to the probability of B. Right? So in other words, it's saying, well, in the first case, probability of A given B, right? If B doesn't affect A, then we just know the probability of that thing happening is the same as the probability of A. Same with the other one. If two events are mutually exclusive, right, disjoint, they cannot be independent. Right? So if they're mutually exclusive, that means they cannot be independent events. If events A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. Excuse me. Pardon me. That moves us into chapter 6, which is the beginning of this semester. Just a moment, I'm trying to remember what time. Okay. All right, in chapter 6, we have discrete and continuous random variables. All right, a random variable takes numerical values determined by the outcome of a chance process. The probability distribution of a random variable x tells the possible values of x and the chances that each of those values occur. It's kind of like a sample space. Discrete random variables have a fixed set of possible outcomes, like 1, 2, 3, 4, 5. Continuous random variables take all the values in some interval of numbers. Right, so a continuous random variable can take any value between 0 and 1. Any decimal, any of that, there's an infinite number of possibilities. If x is a random variable, the mean or expected value is the average of the values of x. Right, we get mu of x equals e of x, which is equal to the sum of x sub I times p sub I, where x sub I would be like it represents one of the outcomes times the probability of that outcome. If we add these things up, outcome 1 times probability of outcome 1 plus outcome 2 times probability of outcome 2, so on and so on and so on until we run out of outcomes and probabilities. That's the expected value. The variance of a random variable, right, sigma squared sub x, is equal to the sum of the difference between the outcome and the mean squared times the probability of that outcome. And again, we add all those values up, and that is the variance. If we take the square root of that value, we get the standard deviation. Once again, you can do some of these things by hand, but you can also have your calculator do some of this work for you. Transforming and combining random variables. Adding or subtracting a constant to a random variable increases or decreases the measures of center and location, mean, median, and percentiles. However, it does not affect shape or spread. Multiplying or dividing a random variable by a constant multiplies or divides measures of center, location, and spread, IQR, range, standard deviation, those are measures of spread, but again, does not affect the shape. And this is why, if we know a parent population is normal, then its sampling distribution is also normal, because the shape doesn't change with any transformation. All right, transforming and combining random variables. If x and y are any two random variables, then the mean of the sum of those two random variables, x plus y, equals the mean of x plus the mean of y, and the difference would be the mean of x minus the mean of y. We're actually using that second one in chapter 10 with our combining or comparing two populations or groups. If x and y are independent random variables, then the variance of the sum of x plus y is equal to the variance of x plus the variance of y, and also the difference of the variances, right? The variance of the difference between those two random variables is also the sum of the individual variances. And again, we use the second one in the chapter we just wrapped up, dealing with comparing two populations or groups. We then also have binomial and geometric random variables, a binomial setting, which allows us to use a binomial random variable. We have to check for bins, binary. Is there all basically it's either true or false, right? It's either a success or a failure. Independent, right? Does the first event affect the probability of the next event? Number, there needs to be a fixed number of trials. And success, there needs to be the same probability of success for each trial. If all those things check out, then we have a binomial setting. If x has the binomial distribution with parameters n and p, n being the sample size and p being the probability of success, the possible values of x are the whole numbers 0, 1, 2, up to n. The binomial probability of observing k successes in n trials is given by the formula p x equaling k is equal to n choose k, which is a function on your calculator. And it basically says how many different ways I can select k things out of n possibilities, right? Times p to the power of k, the number of successes, times 1 minus p to the n minus k, the number of failures. The mean and standard deviation of a binomial or random variable x are mu sub x equaling n times p. All right, so essentially the number of successes, n times p, and the standard deviation is the square root of np times 1 minus p. Right, our geometric setting, right, repeated trials of the same chance process in which the probability p of success is the same on each trial, and the goal is to count the number of trials it takes to get one success. Right, so that's the major difference between binomial and geometric. Is in geometric, we're saying, okay, well, how many times do I need to run this thing before I get a success? Right. If y has a geometric distribution with probability of success p, the possible values of y are the positive integers 1, 2, 3, and so on. It could go to infinity, so that's why there's no end number like in the previous binomial setting. Right. The geometric probability that y takes any value is p of y equaling k equals 1 minus p times k minus 1 times p. And we use k minus 1 because k is the number of trials, right? And minus 1 because if I took k trials to get my first success, I had k minus 1 failures and 1 success, which is why it's p by itself at the end, p to the first power. The mean of a geometric random variable is mu sub y equaling 1 over p. All right, and then we get to chapter 7. Right, sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the population. Right, sampling distribution of a sample proportion. Right, so this is specific to proportions. If we choose an SRS of size n from a population of size capital N with proportion p of success, and we let p hat be the sample proportion of successes, then the mean of the sampling distribution of p hat is equal to p, population proportion. The standard deviation of the sampling distribution of p hat is equal to the square root of p times 1 minus p divided by n. Right. These results are only valid if the 10% and large counts conditions are met. So remember, in a sampling distribution, we only have the two conditions to check. We're checking the 10% condition and our large counts condition. The 10% condition, make sure that essentially if we sample too much, right, it could throw things off, right? And our large counts allows us to use normal calculations if we want to then continue beyond finding the mean and standard deviation to find the probability of getting certain outcomes. Come on. Doesn't want to go. Go. Where are you going? Okay, go. Go. Go forward. You're not going forward. Got stuck. Dang it. Sorry. It's frozen. Sorry, I think I have to restart the presentation. Well, not restart, but like, what time are we at? 1:19. Okay, got a couple minutes left. Let's try to get through just a tiny bit more of this. And I've stalled out. Dang it. All right, well, that's not going to cooperate. I'm not going to fight with that right now. Alrighty. I don't know, Teams is being wonky right now. It froze my presentation, so that's a bummer. Anyway, obviously we didn't finish it. We're in chapter 7 with sampling distributions. We still had more. There's more to that. I do encourage you to look through the rest of that as a review. Again, it's in Canvas under the things you might need module, which is the very first module when you go into modules. I definitely encourage you to check out the rest of that presentation, especially if you feel like you want a little bit more review of the things we've covered. Tomorrow, we're gonna try to do the short demo of the AP testing app, of the short little demo exam. We'll get through what we can of that in the short time we have tomorrow. And then next week we will be beginning chapter 11, and kind of like our last unit, so to say. I'm going to combine chapters 11, 12, and 3 into a single unit, which also means there will only be one more multiple choice and one more free response question self-assessment for the semester, because I'll put those all together as one thing. All right. Is there any questions, comments, concerns, anything like that before I let you all go? All right. Well then, I hope you all have a great rest of your day, and I will see you again tomorrow afternoon.